Today, like Jin said, we're going to be discussing the soil structure interaction model for seismic analysis, demand and capacity evaluation of highway bridges. Basically, we're going to talk for this webinar about demand and capacity evaluation using a 3D model. We'll briefly discuss soil structure interaction and generation of moment curvature. We'll go over nonlinear material properties and plastic hinge properties for members, and a little bit of demonstration of that using MITRE Civil. We'll talk about capacity spectrum method and how we use that to efficiently evaluate our nonlinear seismic response and performance. And we'll go over the model setup, displacement demand analysis. We'll go over displacement capacity analysis. And lastly, we'll briefly look at the AASHTO code requirements. So for the model setup, we'll go over an overview of our model. We'll look at the foundation modeling briefly using MITRE Civil. We'll look at the material modeling, column modeling, and gravity loads. And for the displacement demand analysis, we'll take a look at the model analysis, the response spectrum analysis, and the displacement demand. For the capacity side, we'll look at the displacement capacity analysis for the hinge definitions, the assignment of the pushover model and analysis. And then, like I said, we'll briefly take a look at the AASHTO code requirements. Now for the AASHTO code requirements, we'll look at the P delta capacity requirement check and the minimum lateral strength check. And we probably won't have time to go through the structure displacement demand and capacity check. We won't probably look at the member ductility requirement check or the column shear demand capacity check. But I wanted to mention here that these are important items that we need to look at to complete our seismic analysis and design. And also we'll briefly look at the balance stiffness and frame geometry requirement. I guess so to get started with our model here, as you can see, we have a 3-span structure. The end spans are 54 feet in length, with the middle being 77 feet in length. And we have 4 pre-stressed concrete girders with a spacing of 8 foot 6 inches. And we have an 8-inch concrete deck, and the out-to-out dimension is 34 feet. The beams are continuous over the supports. We have 2 intermediate piers, and the piers have 5-foot diameter columns and are supported on spread footings. The abutments are free in the longitudinal direction and transversely fixed. And so for our foundation model regarding the soils, our soils parameters that we used were G of 1700 KSF and a NEO of 0.35. And at the piers, we could do two things. We could use the general method of spread footings to come up with our transitional degrees of freedom as far as the springs are concerned in the X direction, the translation in the Y, translation in the Z, and also the springs for the rotation about the X axis, the Y axis, and also rotation about the Z axis. And based on our soils properties, we can come up with our stiffness constants over there. And for the PM model, the spring, I wanted to mention the spring used in the demand model. We use the same as the springs that we used in our capacity or pushover model. And also wanted to note here that it is conservative to use a fixed base column to do the capacity model, which is what we did for our bridge here. I also wanted to note over here that Midas Civil is able to generate your springs just based on your soil properties, putting them in our model and coming up with this the soil springs that way. For our apartments, the guide spec, AASHTO guide spec for LRFD bridge seismic design requires that the transverse abutments also be modeled. And so for the girders, since our bridge, we have we modeled the entire bridge rather than having a spine model. So at the girders, at each of these girders, we have assigned joint restraints to them at the bottom of the girders, and we use those to model our abutment stiffnesses. Regarding the material for our structure, we have a deck that's 4,000 psi concrete, and also for the cross beams and the diaphragms, we have 4,000 psi concrete. For the columns, we had 5,000 psi concrete, and our pre-stressed concrete girders were 7,000 psi. Also, for the rebar in the columns, we modeled those as well in order to capture the nonlinear behavior of the concrete as well as the reinforcing steel. And then for other than the columns, we used A709 steel. Our columns, we have 2 columns at each bend, and we used 24 number 10 bars for the longitudinal steel, which amounted to about 1% steel. And in the hinge zones, the columns had confining steel, number 6 spiral bars with a 3.5-inch pitch. The column elements were rigid, so the end offsets were assigned to them at the top of the column and also at the base of the columns, at the footings. And also wanted to note here that the guide spec section 5.4.3 required that we have a minimum of 3 elements defining our columns. In this case, we used 10 frame elements. Right now, I just would like to go over to our model and just briefly take a look at it. And going over to our structure over here. As you can see, here's our bridge with our 4 columns, and I wanted to show it here, I guess, in a little bit of definition. So as you can see, we defined our column members. They have 10 elements in them. We have our pre-stressed concrete girders. In Midas Civil, I wanted to show our links. So we have our rigid links at the abutments and at the piers as well, and also connecting the top of the cap beams to our girders. So going back to our PowerPoint over here, we modeled the columns using Section Designer, Midas Civil Section Designer, in order to capture the nonlinear behavior of the concrete as well as the steel. And we used for the concrete material, for example, here that we're modeling with 5,000 psi concrete, we clicked on the nonlinear tab in order to define the nonlinear behavior of the concrete columns. And here you can see we put in Manda confined concrete properties, and we're able to model the reinforcing and the confinement as well. And based on that, we came up with our stress strain concrete model for the core of the column. And just going back to our Midas Civil model over here, And going to the main menu bar under Tools, the General Section Designer is located right over here. And the tool was kind of useful here in that we were able to go back and forth between MITRE Civil and the Section Designer to put in our column loads and getting our nonlinear properties back and forth from there. So over here you can see our column. You can see the 24 number 10 bars, and by running our section, just takes a couple seconds to run, we would come up with our moment curvature curve over here. And at the top of the column we had a 1200 kip load, and from that we were able to come up with curvature, reverse strain, and moments. So going back to our presentation over here. One second here, okay. For the cupping, the pier cup elements were also modeled as frame elements. So we had frame elements for the columns and for the pier cup as well. And we used, for the girders and the deck elements, we used rigid links to connect the girders to the deck as well as the girders to the capping below. Also, to connect the girders to the capping, we modeled a fixed connection for these elements, as you can see over here. And moving on to the gravity load patterns. For this bridge, we had basically 3 load patterns in the model. The DC of the structure, the DC of the barriers, and the DW for the wearing surface. So in this case, the DC of the structure included the self-weight of the components. The DC of the barriers included just the barriers, and that was applied as a line load to the outermost deck elements. And then we had our overlay, which we applied to the deck elements as well. And so basically here our static loads for our model, we had the self-weight, the wet concrete, the ring course, our wearing surface, and the barriers. So moving on to the displacement demand analysis. Here I wanted to basically talk about 2 items. That is the mass source. And so all of the dead loads were considered as contributing mass to our model. And then the other item is the cracking of the columns, like we mentioned. Section 5.6 of AASHTO guide spec requires that we determine the cracked section properties of the columns. And based on our actual load, we determined 1200 kips was the actual load without including the effects of construction, staging. And for our bridge, we basically found that the staging effects caused very little, or less than 10% change in the actual load. And so it was okay to use this model on our structure. So you can see over here the moment curvature for our column based on our actual load of 1200 kips. And again, this was based on going back and forth between MITRE Civil and the section designer. And we were able to put in our property modifiers from the previous moment curvature that we just looked at. And also I wanted to note here that the torsional constant modifier set by AASHTO guide spec is 1.2 for the columns. So that's what we used on our model. And then as far as the mass participation, AASHTO guide spec requires that section 5.4.3 requires that 90% of the mass participation be captured in both directions, longitudinal and transverse. And we were able to obtain that for our bridge. And also for our bridge, the mass was considered to be the same in both directions, even though the end diaphragms were modeled as free in the longitudinal direction, and we restrained them transversely. And then moving on to our seismic response spectrum, now we were ready to get our spectrum acceleration. To do that, we used Midas Civil. This can also be done based on the mapped coefficients that you get from the location. Our bridge was located in Ridgefield, Washington, and the PGA there was 0.256 G. S of S was 0.605. S1 was 0.217 G. And the side class there was side class E. And so our FPGA came out to be 1.422, FA 1.489, FV 3.129. And from these values, we were able to get our response spectrum using the A's of S of 0.364, SDS of 0.901, and SD1 of 0.679 G. And since our S of D here was greater than 0.5 by the guide spec table 3.5-1, our category came out to be D. And just wanted to get back onto the onto the Midas Civil to show how we came up with the spectrum. So in our model, first of all, we had to convert our cell weight into mass, as well as some of the dead loads into mass. So to do that, for the self weight under structure, we went to structure type, and very easily here we converted the cell weight into the mass. Similarly, for the dead loads, we went over here and in the Midas main manual to load and load to masses. And we had the barrier, and we also had the wearing surface that we wanted to convert to mass. And simply by converting those loads into mass, we were able to get our modal masses. And you can see here that all those had been converted into mass. And then to do the analysis, we went over here to load seismic, and we first had to define our response spectrum file, and we used the H2LRFD to define our spectrum, H2LRFD 2012. And based on our soil properties, PGA, S of S, S1, and response modification factor 1, we came up with our response spectrum, as you can see over here. And after that, once we had our response spectrum, we moved on to the define the load cases. And for model, we defined two load cases. RSX was the load case in the longitudinal direction, and then we also had RSY for the transverse direction. And you can see both of them were defined here. So going back to our PowerPoint here. There's our response spectrum, just like I showed how we came up with that. And how we set up our load cases, the two response spectrum load cases, one in the longitudinal and the other in the transverse direction. Also wanted to note over here, by the guide spec, we're required to do a combined quadratic in order to perform our model analysis, and that's what we used. And moving on to the spectrum analysis, for the load case in the Y direction, I just wanted to note here that the only thing that we made different there was that we changed the direction to 90 degrees, which made it go in the transverse direction. So now for the displacements, we ended up tracking the displacements at the top of the column, as you can see over here, and that was joint number 229. And for the longitudinal direction, based on RSX analysis, the displacement in the X direction ended up being about 7.5 inches, and in the transverse direction, UI was 0, based on RSX. And in the transverse direction, based on RSY, we came up with a UX of 0.17 inches and a UI 3.55 inches at the same node that we tracked. So we now had to perform a displacement modification based on section 4.3.3 of the guide spec, and for that we had to compute T's of S and T's of T. And based on these equations, we came up with a T's of S of 0.75 seconds. T star was 0.942 seconds. And so for the longitudinal direction, the modification was just about 1, and 1 is the cutoff, so we said, well, we're going to modify that. And then in the transverse direction, our modification came out to 1.45. 1.54 was greater than 1, so using our equations here, we came up with a modification factor of 1.45. The column displacement demand, section 4.4 of the guide spec requires that 100% plus 30% of the displacement for each orthogonal seismic load case be combined. And so, again, tracking our top of column joint 229, for the longitudinal direction, we came up with a displacement of 7.55 inches based on our 30%, 100% rule here. And then for the transverse direction, we came up with a Y displacement of 5.45 inches. And you can see over here, moving on now to the capacity analysis, plastic hinge definitions. At the tops and the bottom of the columns, we found we had enough moment fixity for plastic hinges to occur. And this was based on our actual force diagram, as you can see over here, based on just the dead load, DC and DW. And at this point, we had to define our and assign our plastic hinges. And to do that, we used the MITRE Civil section designer, and from our moment curvature, based on 1200 kips, like I had mentioned before, we came up with our moment curvature relationship over here. And the clear height of the columns being 350 inches, we computed L1, or the length from the point of maximum moment at the base of the column to the inflection point, to be 176 inches. And L2 for the top of the column came out to be 174 inches. So in order to assign the plastic hinges to the column elements along the column frame, we computed a relative length of 0.30 in the at the base, from the base of the column, and then for the top of the column we computed a relative length there of 0.51. And the plastic hinge length then must be computed at both the tops and the bottom of the columns, and we used the AASHTO guide spec section 4.11.6 equation, as you can see here, to come up with that plastic hinge length. So based on 80% of the length of the column from point of maximum moment to point of contraflexure, and 15% of the expected yield strength of the longitudinal column reinforcing bars, and multiplied by the diameter. We had 24 number 10 bars, which was 1.27 inches. And we came up with LP1, plastic hinge length at the base, to be 27 inches, and at the top, almost 27 inches, 26.91 inches. And so we had to define our plastic hinges in our Midas model. And I'm just going to go back into Midas now and just quickly show how we did that. And to do that, basically we selected our columns over here, which was pretty simple in Midas, and that was by going to our section. And that was up here. And then basically all we did was come over here and assign our by dragging and dropping, we're able to assign the plastic hinges to our columns. So going back to our presentation over here. One second, there we go. Okay, so the longitudinal direction, the lateral load distribution used for the push-over analysis in the longitudinal direction is a direct horizontal acceleration, and that's how we define it in Midas Civil. So we assigned a uniform acceleration of in dx direction, and I will go back here in just a little bit to show how we did that in Midas Civil. And similarly, we did the same thing in the transverse direction. And also wanted to mention over here that our dead load must be applied prior to performing the pushover analysis. And to do that, if you recall, we had defined the self-weight, a wearing cost, and a barrier, and these loads existed. So in order to continue analysis, we had to use import basically our static analysis with these load cases and carry on from that pushover analysis. And I'll just jump back right now into my Civil just to show how we did that. So to do a pushover analysis, this is the general tab for Midas again, and we go to pushover here, and we have the Midas global control. And here is where we do all the global controls. Over here we can assign the self-weight, the wearing cost, and the barrier as an initial load case, and that will be carried on from where we are in order to do the pushover analysis. We were pretty confident that our model, we were not going to go into nonlinear just based on the self-weight and the wearing cost and the barrier dead loads. And we were pretty confident we can just use the import from static analysis mode here. Also here you will see there are some other menu items here that you can do iterations here for nonlinear analysis option. You can also stop, if you expect some yielding to occur, you can stop the analysis. And there's also some other features here I just wanted to point out as well for pushover. After we assigned our global initial loads over here, then we went over to the load cases. And then the load case and the pushover load cases, we assigned displacement in the x direction. I will just show that real quick here. We call that push x, and we had 20 steps. And our expected, we had a maximum translational displacement, if you recall, of about 7.5 inches, and we put in 8 inches here as our maximum translational displacement in the x direction. And similarly for the y direction, we put a displacement here. I had 16 inches here, should be 8 inches. And that set our displacement. So going back to our PowerPoint. It keeps moving out of there. 1 second. There we go. Bear with me for a second here while I get this one. There we go. Okay. So after we had our load cases set up here for pushover analysis, as I mentioned, we ran our analysis, and in the longitudinal direction, we came up with the pushover curve. So our pushover curve, as you can see here, looks like so. And our capacity basically was right over here where the curve changes. Similarly, we did the same thing for the y direction. And I will just show over here, after we run our analysis, what our model produced as far as the plastic hinges. So I will go back into our Midas model over here, and I will open this model is not run. I will open one that has already been run in order to show that. It takes about 30 seconds to run the model. I didn't want to go through that, so I'm just going to open one that has already been run over here. And so you can see our structure. See if I can move this out of the way. So on the pushover, we can get our deformations. Push X is our load case. We want the displacement in the longitudinal direction, and I'm going to show the legend here, and I hit apply. So right now you can see the blue means the plastic hinges have not formed at this point. This is step one, and as we continue to increase our steps here, our push loads, you can see now the step 5, the plastic hinge has started to form here at the bottoms of the columns. And we can continue, if we just continue that, you will see additional plastic hinges forming at the top of the columns as well over here. So going back to our presentation over here. Get this out of the way. So again, in the transverse direction, we did a similar analysis, and that was for push Y, and we looked at the displacements in the Y direction, and the location again was right at the bottom of the columns is where we started forming plastic hinges. And so at this point, I wanted to briefly go over the code requirements. The first one being the P delta capacity requirement check per section 4.11.5 of the guide spec. And for that requirement, we needed to satisfy this equation here, where the unfactored dead load of the column, which was about 1,200 kips, needed to be less than 25% of the plastic moment, or the idealized plastic moment capacity. And that, based on our column material properties that we computed with the section designer, was about 78,560 kip inches. And so in the longitudinal direction, we computed 25% of our plastic moment, came up to be about 20,000 kip inches. And we computed the PDLR of 56 kip inches. That came up to be less than 19,640, and we were okay there. Again, now in the transverse direction, similarly, we computed a moment of 3648 kip inches, again less than 19,640 kip inches. Again, we were okay. The other code requirement check that we made was for the based on section 8.7.1. In that one, where we needed to satisfy the normal moment capacity of the column based on the again the material properties that had to be greater than 10% of the dead load of the column, force associated with the tributary seismic mass collected at the bend, multiplied by the height of the top of the footing to the top of the column, which was about 408 inches, plus 0.5 times the depth of the superstructure. In our case, was 85 inches, and all that divided by a fixed factor based on section 4.8.1 of the guide spec. For columns, we had 2 for top and bottom being fixed. So to determine M&E, section 8.5 of the guide spec requires that we use a concrete strain of 0.003, and so we used section designer in minor civil to determine M&E based on our strain of 0.003. And I will just jump back into section designer here real quick. Here we go, section designer, and our column. Just run that real quick. And as you can see here, we had 1200 kilo. And let me just go back over here and edit this real quick. Stress strain curve. So basically, let me close this. Basically, I wanted to demonstrate where we come up with our moments. Let's go to the moment curvature again. So we looked at our strain of 0.03 over here, and that's where we came up with our moment. And going back into PowerPoint, our M&E moment here was 73,482 kip inches. And here's a better slide. Actually, you can see our maximum strain 0.003, and scrolling down over here is where we come up with our 73,482 kip inches. And so having our moment, then we had to determine P tributary. And since our abutments were modeled as free in the longitudinal direction, all of the seismic mass was collected at the bends or at the piers, and therefore the force associated with the tributary mass collected at the bend had to be greater than the dead load per column. And so we computed that based on the weight of the structure, the number of bends, number of columns, and we came up with 1660 kips. And so to perform our check, we came up with 37,393, which was less than 73,482 kip inches. And again, we were okay. Here I wanted to mention that our structure was relatively symmetric, and so just by observation, we were able to say that the balance stiffness geometry check was okay just by inspection based on our structure. But also want to mention that for structures that are not symmetric or where you have bends that are not identical or not similar, this check sometimes might be a controlling factor on your bridge. And that's an important check based on the geometry of the structure. Also, the other checks that are required are the structure displacement demand capacity check, the member ductility requirement check, and the column shear demand capacity check. Those items are due to time are covered elsewhere, and we were not going to discuss those at this point. And with that, I just wanted to acknowledge Midas Software and Ashto